Welcome back to Comp 526, Efficient Algorithms. We're starting with the second part of Unit 0 and look at some proof techniques. These are some prerequisites that we need to digest some of the statements we make about algorithms and data structures later. Although this unit will not really contain much algorithms and data structures, we take one further step away from that. So this is just about logic and mathematics, but you'll see where it comes back to programming towards the end. I listed a few learning outcomes. You're supposed to know some proof strategies, and it will become clear what these are. It's a given list of things. There's certain types of statements, and each comes with a strategy how to prove it. That's just the scaffold for a logical argument. You still have to fill in the gaps. Specifically, one that's particularly important in computer science is called induction. We'll talk briefly about this later. And we'll apply proof techniques very briefly to give you a glimpse of how you can prove a program correct and what that means. We'll only touch on this very, very briefly. But I think it's useful to know roughly what the limitations and possibilities are there. Before we start with the actual proof techniques, I want to take a slight digression and actually do look at one algorithm. And you'll see also the type of code I'm using on the slides mostly. And this is just as kind of a backdrop for what's to follow. So without much introduction, let me say we have a goal to shuffle an array of numbers. So there's a few things I should maybe point out. This is my notation for arrays. So what is an array? An array is a contiguous piece of memory filled with data, and all these individual data items have the same size. We also usually think of them to have the same type, but some languages don't fuss about that so strictly. But here I'm specifically saying it's numbers. So if you have programming background, think of a C-type int array. That's fine for this purpose, although the algorithm doesn't care too much. The second bit of the notation is this convention for indices. Arrays start at 0 in this module. It's just the computer science way of thinking. It's a pointer and an offset. That's where this comes from. So if we have an array of n numbers, it starts with a 0, and then it goes up to a n-1. And to not always have to write the -1, I'm using this round parenthesis to say that's exclusive, the endpoint, and the 0 is inclusive. If you come from C++ and have worked with iterators and pointers there, it's quite natural to work start point inclusive, end point exclusive. If not, it's a bit of nerd weirdness to get used to, but it's consistent in this module, so it's worth getting used to it. Right, so that's an array of numbers. And one first thing to note, n is just any variable. I want this to work for any size of an array. And the goal is to randomly reorder the array. So shuffle here means you're given an array of numbers, and afterwards it should be impossible to know what the original order was because you just completely randomly rearranged all the numbers. Implicitly, what this says is it should still contain the same numbers, the same multiset of numbers, just in some different order. So we expect algorithms to basically swap two elements. That's the key thing that an algorithm can do, to rearrange elements. Take two indices, take the element here out, take the element there out, put them back in the opposite order. Okay, I mean, this was maybe baby steps for some of you, but bear with me a bit. Now that's a task that arises in various applications. In data science applications, you may often want this to kind of avoid any bias from the initial order of the list. Say you're writing some survey software and you want the answers to appear in random order for each participant. All sorts of things, fairly natural to come up with. more examples. And here's some code that might achieve this. And before we dive into what the code does, let me try to briefly explain what this kind of pseudocode looks like. It's not real code in any programming language. I don't know any compiler that would eat this and spit out a computer executable. But it's fairly close to many languages with slight superficial changes. So I'll write procedure to say this is definition of a function. It's maybe a bit closer to old languages like Pascal. Python would just be def, right? Then there's the name of a function, and it takes some parameters. I'm not usually strict with typing, so that's maybe Pythonic then. Close to what Python does. They don't care about types as much. So there's one parameter of this shuffle function, namely our array. Not a big surprise, I hope. And then we can write different things in pseudocode. So for example, for loops, right? They just go through what is indented further for every value of I in the given range. We have other function calls, and in this case, I'm calling a function random int, and I'm just assuming, postulating that this function exists. And the comment here in English just tells you what I'm hoping this does. Most programs have some assumptions like this, and it's super tedious to always have everything on the slide, and you couldn't read it. So we'll usually work with something like this. There's some things we just assume given, and then we work based on that. And here's the swap operation that I explained before. We expect an algorithm to use this here, and here it's just writing, take the position I and take the position R. These are two variables. They have some integer index in the array. Take the elements and swap them, right? I hope that's fairly intuitive to follow. I also hope that at least by the end of the term, all of you would be able to take this pseudocode and code it up in Python, hopefully a bit earlier than by the end of the term for this simple thing, or take another programming language. This is my approach, to be a little agnostic to what language you come from. Good. So that's about the pseudocode, how we write algorithms. Now, what does this actually do? Well, it looks at each position in the array. That's basically the I. And then it finds a random position for that element to go to, and it swaps it there. Sounds good? That should put it in some random order. Now, okay, let's just do this. See what you could come up with. Oh, Slido is slow today. I had 64 people saying they got the attendance code. So maybe we can crack that up, and that number in the corner. Maybe we can get that at least to 65, 60, 64. Same as before. There's probably a few more in here. Okay, let's define 65 is my goal. And let's briefly just see what you came up with. So a lot of you have seen something like this before. That's great. So you can deal with the code. Not so many are sure about this, it seems, right? More people are confident about the last part. That's the longest statement, right? If it's convoluted in the formulation, it's usually the right answer. So let me lock the results for now and switch back. Yeah. You mean the last two parts, D and E? Depends how picky you are.
Like, okay, the second, no, E is going to be like a strict subset of E. So like, if they have the same probability, they have equal probability. You can't have like ordinary with equal probability, or then they have the same probability. E just seems like a more overrated embodiment. Confused why many people are content of E for fear of content of E. It's like the same statement and same.
Yeah, okay, I get your confusion. So the point was, it sounds like E is a subset of D, and you're right. I mean, I've slightly reformulated this to make it sound a little confusing, but you're very right. And so it's kind of surprising that more people ticked E than D to you. Is that what you're saying? Well, it's a subset in the sense of the statement. So it could be that E is true and D is false. In principle, that's possible. In our specific case, D and E really is the same because I'm assuming that this random int does the right thing. That's not the trick of this question. The trick of this thing is something else. And let's have a look at this. So how would we take a step back, forget about the question for a minute, I'll come back to it. But how would you even approach saying that this code does the right thing? So what is the right thing? Yeah.
For each element in the list, it swaps it with a random.
Sure.
Yeah.
Each element is swapped with a random
So if you
position.
assume that a probability distribution between in 0 and n, then and a uniform probability distribution between 0 and n, that's like what? Let's say uniform random means that for each number 0 and n, random int produces splits each number up into the same uniform probability. So
right.
1 over n. Then for each element ai, for each a in the sequence, the probability of them occupying each, getting associated with each r, with each number is the same uniform probability. So for like the first element into this, probability of it getting mapped to any number between 0 and n is the same 1 over n probability.
Let me try to summarize this for the live stream. So you're saying this random int gives a uniform number in this range. That's exactly the assumption. And so it seems that every element should be at a random position, and the overall thing is uniform. Now let's look at what happens. So if you take two different elements, that's the easiest kind of thing that is at least doing something. There's two possible outcomes, and these are listed here. And what these bars show is the relative probability of them becoming the result of this function. And it doesn't matter how you start. So you could start with a sorted list if you want. Now, if you do this for 3 elements, something weird happens. So this is starting from the sorted list and then calling this algorithm many, many times and looking how often you've seen the different outcomes. And it gets worse and worse. And then I ran out of space on the slides, but you can continue this. You can even analyze this and show that in a way the relative error. So if this red line, one sec. So the red line is basically the uniform that you would want to see. And so the difference between the peaks and this line become even worse. Yeah.
Is this like a problem because the even n is small? Does this like converge to uniform probability?
Nope. It's not converging to uniform. It's not a problem of small n. And it's even worse. It's kind of diverging from uniform. So there's some things, some orderings that relatively speaking, the probability of them coming out compared to what we want, the uniform 1 over n factorial, that relative difference grows with n. is completely broken. It's startling, right? It looked so well, and I mean, those of you who know this, they might have immediately seen the argument. So I don't want to spend much more time proving to you that this algorithm is wrong. A simple way to do it is to count the number of possible outcomes. That's a nice, rigorous way to show it. So here we're taking n random numbers, and each has a range of n. That's n to the n different things. But what we want is uniform over n factorial. Just by pigeonhole principal arguments, this cannot work out. But this is not what I want you to take from this. The thing is, for showing that the algorithm is broken, all that's on the slide is enough. It doesn't work for 3 elements. What the, right? I mean, that's not good. Even if it's fine for larger inputs, this is surprising, and we don't like an algorithm to be wrong. And so even if an algorithm looks really intuitively correct, it might be broken in fundamental ways. And so we really want some machinery to be sure. That's what this unit is about. And well, to make that point really clear, never use this. I'll show you the correct one in a second. And so in terms of this question, you can see how you did. I mean, this is true for me, so the first two are not relevant, but it's true that the algorithm can produce every possible ordering. With some probability it does, but neither of the other two statements are correct. The fix for this is super simple. It's a single symbol you have to change. Instead of 0, you put an I here, and then it works. Intuitively, why that is so different, think about how a single element can travel. In the original algorithm, it could be swapped several times around if it gets selected again. Whereas here, we go through every element, and then for each position I, we now decide which original element is going there. And then once it's there, it's never touched again. Because I goes up, and we don't have R below I. So after we made this swap, so for each element, we have one point in time where we decide, this is your final value. Chuck. And then it stays there for good. That's why this algorithm is good. That's why this bears the name of 3 famous people. It's usually called the Fisher-Yates shuffle. Knuth popularized it. They all deserve credit for many things. This is a fairly simple algorithm, so maybe it's all right. But that's the name it goes by. So if you ever need to shuffle, look for this one. Don't use the other one. So both of these algorithms look intuitively fine, but they lead to different outcomes. So we really want some way to tell them apart. The way to tell them apart relies on formal proofs. And there, the first step is formal statements, logical statements, and then how to arrive at the validity of such statements. So if you want to go all the way back, this is the very question that mathematicians answered in the 20th century. Only in the 20th century, somewhat remarkable. What does it mean to have a proof? Prior to that, a proof was, if it was convincing to your fellows, the other mathematicians in your guild, then it was good. And if it wasn't convincing them, it was not good. But this relied on people to be diligent enough or apply enough scrutiny to these arguments. And in the 20th century, some of the big successes are putting maths on a formal foundation and discovering the holes in there. There's some fun story around impossibility results. But what we do have is a clear understanding of what formal proofs are. And if you can prove it in that system, it's bulletproof. That's why I have this little Iron Man for the unit as well.
Isn't it possible to prove some things that are not true?
Is it possible to prove things that aren't true? That would be really bad for a formal system. There's many examples of things that look true and look like provable.
Fully aware, but I've heard that Peano arithmetic and Peano arithmetic is inconsistent. Peano arithmetic is like it's not Peano arithmetic cannot prove its own consistency. So depending on other assumptions you make, you can like prove previous things, and there are things that are true and not provable, things that are not true and provable. I don't know if I'm
Okay, so you're getting at consistent and complete systems.
Yeah.
Let's take this offline. We can chat about this afterwards, because I think it's for most people doesn't help much at this stage before we talk about other things, and it's beyond the module. But there's some really cool math theory behind this. It's a lot of fun. You don't need to worry about it for this module, but it's definitely worth knowing. I can talk about this at the end of the slot. So what we need, a formal proof is written in a formal system, and that tells you what kind of statements you can write to make proofs of. And so a formal proof is a sequence of such statements. And each statement can either be an axiom. That's something that everyone decides we believe in that because we decide to believe in that. There's no justification beyond that, but they're usually so clear and primitive that they're fine. And this is not usually a problem. For the experts, axiom of choice, there's some that are debated, but this is on the philosophical and esoterical end of mathematics, I'd say. There's a set of axioms that people rely on, and there's no doubt about them. And we can restrict ourselves to those for this module entirely. So and the statement is either an axiom, something that is true because everyone decided, let's rely on this, or it is something that follows from previous statements using a set of rules. And we'll see some of these in some of the example proofs. But these two things together imply if you start from valid axioms and you apply valid rules, everything you'll ever be able to write down is valid by definition. And so there's no interpretation needed or no human scrutiny needed. Some of these systems are provably incomplete, so they're true things that they cannot show. That's a bit annoying. But if you have a proof, it's not a problem. The proof is valid and the proof is rigorous. It's just sometimes you need to go outside of a specific system. So that becomes relevant if you want to prove things automatically by a computer. But that's not our topic for this module. We'll usually actually go back to convincing humans because going to this level of detail is very, very tedious. I want to convince you in this unit of that fact, and also try to show you how you can live on a slightly more abstract level, but keep the possibility of going all the way down if you have to. For example, to check in cases like for this shuffle algorithm, where it seemed to work fine, but if you look close enough, you notice one does and the other doesn't. Good. Okay, let's dive into some of the statements that we can make. And I'll use English language examples here first, just because it's a little easier to talk about. But we'll mostly have mathematical statements here later. So we can have statements. What's a statement? A statement is something you say that can be true or false. We'll usually not allow anything between. It's either true or not true, which is the same as false. Okay, there's no gray areas. And so a great example is it rains, which is already debatable if that's always either true or false. But let's pretend, right? You formalize that in some way if there's any drops reaching the ground, or I'm sure this gets hairy if you define it properly, but let's ignore this. Humans are usually good at having a sort of some vagueness we can tolerate well. A second statement can be the street is wet. Similar problem, but let's pretend this is very clear and always true or not true. If we have a statement, we can negate it. Then instead of the statement, we have not the statement. So not A is not it rains. We usually say it doesn't rain. logically the same thing. We can put and or between two statements, A and B, it rains and the street is wet. Both have to be true for the whole thing to be true. And or means, well, either of them can be true. It's okay if they are both true. So this is not an exclusive or. Sometimes it's useful to have the statement it's either A or B, but not both in one thing. As you notice, English doesn't really have this. We often use or in the sense of exclusive, not both, but not always. And if you want to be very clear, you have to wiggle your way around and say it explicitly, either A or B and not both. It's sometimes convenient to have a notation or an operator for that, and XOR is the thing that people use for that. I don't know if we'll ever use this. I've seen this notation many times for Boolean logic reasons, but well. So this statement is true. A, X, or B is true if either A is true or B is true, but not both. And also not both false, please. Clear? Okay, the more interesting ones are implications and equivalence that builds on it. Implication is written as this, A arrow B. A implies B. In English, we would say if A holds, then B also holds. Something like that. If A, then B. And this is really equivalent to not A or B in case of doubt. We'll come to that, but here, if I insert what A and B means, it becomes relatively intuitive. So if it rains, then the street is wet. Sounds good. Equivalence is one step further. It says A and B are really either both true or both false. So A equivalent to B means A holds if and only if B holds. And because this is something we use so often, mathematicians have invented this if with a double F to mean if and only if. Just the if is implication. The only if, A only holds if B is true, is kind of the reverse implication. So that's why you can also define this A equivalent to B by having both implications. A implies B and B implies A. Yeah, question?
About this.
Yeah.
Okay, so if you have like two statements, P and Q, A and B, then if A is a necessary condition for B, then I say A implies B. That's what it means when A is a necessary condition for B. Then if A is a sufficient condition for B, then B implies A.
Yeah, okay, so these are two useful terms, necessary and sufficient conditions.
If A is a necessary and sufficient condition for B, then A if and only if.
Yep.
Yeah, and another way to think of it is if A implies B, then the set of statements where A is true is a subset of the set of statements where B is true.
Yep.
Right? And vice versa. And if, yeah, that's like, I find it an easier way to think of implication and equivalence.
Yeah, that's right. So there's alternative names for these if you want. A implies B. We sometimes say A is a sufficient condition for B. If A holds, then B already holds. And the other way around, B is a necessary condition for A. If A is supposed to hold, then B better also hold. It's another way to phrase it. I mean, yeah, it's more intuitive for some people, and others like the implications more, or you think in terms of Venn diagrams. You have to find your way. It's something that this book gives you all the different variations of, and you can pick whatever you find more intuitive. Now let's do a little exercise on this one. Where's the question? Sorry, now it's showing. It's annoyingly slow. I don't know. Slido has a problem today. I should have probably hidden this. All right, let's have 65 again. I hope we don't have too many flat earthers in here. All right. Show it again. Okay, well, because I give participation marks, I shouldn't lock the questions too early. So it's roughly 2/3, 1/3, maybe a bit more for yes, but a few for neither as well. So this is a true statement in the logical sense. And the good thing is it doesn't depend on whether you believe the Earth is flat. It's simply implications are always true if already the premise is false. And that becomes obvious if you say, let's decompose this into our statements. That's statement A. If A, then statement B. Now maybe we can agree that B is not true, but doesn't matter. A implies B is the same as, maybe I'll write it like this, not A or B. That's just the definition of implication for us. That's why I'm bringing this question. So if A is false, and we believe A is false, it doesn't matter what B is. If B is true or false, we don't need to care.